Hi again, guys. So this next video is going to get into what redox reactions are useful for. We just had a lot of stuff we had to understand about them first before we can really get into their uses. Basically, a redox reaction is the reason why a battery works. So this picture, this is called a voltaic cell or a galvanic cell, which is a type of electrochemical cell. And this is a very large scale model of what inside of a battery looks like, or really how it works. So in this diagram, and these are the diagrams that you guys are going to see, you're always going to have, sorry, that was supposed to be an underline. You're always going to have two beakers. And in each beaker, there's going to be a piece of solid metal called an electrode. That's just a word for a piece of metal. So in this specific electrochemical cell, I have zinc in one beaker, and then in the other beaker, I don't know why it's not showing there, it's just very hard to see, I have a piece of copper. So those are going to be my two pieces of metal. The metals are in aqueous solutions that have ions of that metal floating around in it. So the zinc electrode is in a zinc sulfate solution. So there are zinc ions floating around in this liquid. Over here, my copper, I'm going to just change the color so you could see it. My copper metal is in a copper sulfate solution. So I have copper ions floating around in this solution, and that's going to be important later. The pieces of metal are connected by a wire, so that is this right up here. On the wire, this says it's a galvanometer, or usually it's called a voltmeter. So as electricity runs through the wire, it measures how many volts of electricity are being produced. So that's what the wire does. So that's an important part. And then we have a salt bridge, which is this right here. And it's a U-shaped piece of glass tubing that connects the two beakers. And inside of that salt bridge, there's like a solution of ions in there. And the ions flow back and forth. And their main job is to keep the solutions neutral. So we'll get into how they do that in a little bit. Okay, so the first thing we have to do is we have to think of what my two metals are, and we have to look on table J to figure out which is oxidized and which is reduced. So back in my notes to table J, I have this circled from before. I have zinc up here, and I have copper down here. So this is all voltaic cells are spontaneous reactions, meaning they follow table J rules. So zinc is the higher metal. So what should happen to zinc? It should get oxidized. So I'm just going to write oxidize over here, meaning get reduced. Now, something that you're going to need to know, we give you a sentence to kind of help you remember this, but the sentence is N ox met a big red cat. An ox met a big red. So where oxidation is occurring, that piece of metal is called the anode. So more specifically, just saying zinc is an electrode, we say it's the anode, and that specifically tells us that that's the piece of metal getting oxidized. So an is anode and ox is oxidation. Big red cat, we'll get to the big later, but red cat stands for reduction cathode. So where reduction is occurring over here, this piece of metal is more specifically called a cathode. Now we know it's a piece of metal that's getting reduced, not just any old piece of metal. Okay, so that's going to actually come into place later, but I thought it was good to mention now. Okay, so we figured that out. Okay, write the half reactions for each metal. So guys, if you think about it, I have zinc metal, which has an oxidation state of 0, and I have zinc ions floating around in solution. So is zinc going from 0 to +2 getting oxidized, or is zinc going from +2 down to 0 getting oxidized? Oxidized means that the oxidation state has to go up. So down below this half cell where they give us this double arrow, I actually want to just show it in this direction. Zinc is turning into zinc plus 2 and by losing 2 electrons. That's what oxidation looks like. Okay. My reduction half reaction, I want to think about copper over. So copper metal has a charge of 0 and copper ions have a charge of plus 2. So which way is getting reduced? From 0 to plus 2 or from plus 2 down to 0? Going from plus 2 down to 0 be getting reduced. So that's actually what's happening in this electrochemical cell. One thing gets oxidized, the other thing gets reduced. Okay, so now the wire is where electrons flow. When zinc loses electrons, those electrons go up into there and they flow through the wire to the cathode. So anode to cathode is always that the electrons flow, no matter what the two metals are, because they always flow from the thing that's losing to the thing that's gaining. Okay. There's actually a mistake here, guys. The anode is negatively and the cathode is positive charge. So when you think about a battery, you know how there's always a positive and a negative end? The negative end is the anode and the positive end is called the cathode. So a way to help you remember this, the word anode has an in it, and the N can help you remember that the anode is negative. And if you look at the word cathode, the T in cathode kind of looks like a little plus sign. So the cathode is always the positive end of the battery. It's where reduction is occurring. Okay? Great. So now we're going to talk about the size, which is where Big Red Cat comes into play. If you think about what's happening at the anode, as zinc loses electrons, it turns into zinc ions. Where do the zinc ions go? They fall into the solution. So you literally have pieces of metal ions and dissolving in the water. So what's going to happen to the anode every single time? It's going to lose mass. It's always going to get smaller. Okay, you don't want to say because it's losing electrons, because electrons don't have mass by themselves. But what happens to the zinc atoms when they lose electrons is that they turn into ions and they go into that water. So they're no longer solid pieces of metal sitting there. If you took out that metal and weighed it, it would have less metal on it, so it would be lighter. Now, if you look at what's going on the copper side, Big Red Cat, the cathode always gets bigger. It always gets heavier because look what's happening. I have copper ions floating around the ocean, and I have electrons coming over to those copper ions. What happens to copper ions when they pick up electrons? They literally turn into solid copper atoms. And those new atoms that you're making, they stick to the metal that's already there. So your cathode, it's getting more metal added onto it, and it's always going to get heavy. So that's what the big stick cat. Okay. Now the salt bridge. It doesn't matter. It doesn't matter what kind of salt is in the salt bridge. It could be anything. I'll just do NaCl for simplicity's sake. Okay. Now, if you think about what's going on over in the zinc half cell, okay, as the zinc oxidizes, I'm getting more and more positive ions in solution. So if too much of a positive charge builds up, the battery's going to stop working. So one of the ions in the salt bridge has to go to that zinc beaker and even out those positive charges. So what evens out a positive charge? A negative charge. So anions from the salt bridge always go to the anode half cell, and that's going to help balance out the charges and keep everything neutral. The opposite happens over here. These copper plus 2 ions, they're turning into metal and they're sticking to the piece of metal that's already in there. So I'm losing positive charges over on this side. These ions are turning into metal and they're going there. So what in the salt bridge can come over and help replace the positive charges that we're losing? The sodium ions, or whatever in salt bridge. They're always going to go to the cathode to help keep everything neutral. So for you guys, you're responsible for knowing which ion goes where. For the reagents, all you have to know is that the salt bridge's whole purpose is to allow ions to flow. And it really shouldn't say in the same direction as the flow, because the electrons only flow in one direction. They always flow anode to cathode no matter what. Where in the salt bridge, you have ions flowing in both directions. That's important. Both directions. So just before you guys do some practice questions, I just want to show you, let me get out of this screen here. Okay, this is actually a really good animation. Unfortunately, the zinc and the copper switched places. The zinc's over here and the copper's over here. But it's a really nice animation showing how electrons leave the zinc metal and they travel through the wire and they go over to the copper. Now, if I click and zoom in on the zinc, it shows that as the atom loses 2 electrons, the zinc turns into an ion and it breaks off and it dissolves in the solution. So you can literally see it getting smaller, which is kind of nice. Okay, you can see the positive charge increasing, which is why if I look at my salt bridge, see how I have negative ions going to the left? Negative ions are going to cancel out those positive ions that are being created in the left beaker. All right, if I go over here to the cathode, I have those blue copper ions floating around in the solution, and as they pick up electrons, you see they turn into copper atoms and they stick to that piece of metal. And that piece of metal is just going to get bigger, bigger, and heavier as ions turn into atoms. Now, because these positive ions are leaving the solution, if we take a look at the salt bridge over here, look at what's going to the right. See how positive ions are flowing to the right? Positive ions are going over there to replace the ones that left. Okay? Now, eventually, this zinc electrode is going to completely dissolve. That's when your battery dies. That's when your battery stops working. If you think about rechargeable batteries, we'd have to force this reaction to go backwards to refill the zinc metal again before we can use the battery again. So that's something that's not spontaneous. That's something that won't happen naturally. That's something we're going to talk about a little later. So one more thing I want to write on your notes, guys, before I let you out of here. Let me make this a little bigger so you can see it. Okay. I just want you guys to write down that the voltaic cell, it's spontaneous, which means all on its own, it follows table J rules, and that we have, because we have a chemical reaction, making electrical energy run inside a battery. All right, so that's it for next time, guys. I'll see you in a couple days.